Picture this: you're drifting through space, weightless, staring into a void so deep and dark it seems to swallow the very light around you. Just ahead, the fabric of space-time twists violently, warping reality itself into an inescapable spiral. This isn't science fiction, it's the edge of a black hole's event horizon, one of the most extreme gravitational forces in the universe. And in this moment, you'd be witnessing gravity's raw power, bending the rules of physics as we know them. But what if I told you black holes are just the beginning? That the cosmos is filled with even stranger, more violent displays of gravity forces so intense they can rip stars apart, slow down time, and reshape the entire universe. Gravity is the silent architect of everything we see, the reason planets orbit, stars shine, and galaxies spin. But beyond the gentle pull we feel on Earth lies a realm where gravity becomes something else entirely. A realm where it's no longer just a force, it's a cosmic monster. Think about the sheer power needed to crush a star into a speck smaller than a city, or to twist light itself into a ring. These aren't just abstract ideas, they're real phenomena happening right now, millions of light years away, in places where gravity's extremes rewrite the laws of nature. And today, we're diving headfirst into that chaos. Over the next 30 facts, we'll explore the universe's most jaw-dropping gravitational wonders. From neutron stars so dense a single teaspoon would weigh 1 billion tons, to supermassive black holes that command entire galaxies. Each revelation will leave you questioning everything you thought you knew about gravity. We'll uncover how these forces shape the cosmos, how they challenge our understanding of reality, and perhaps most thrillingly, how scientists are racing to unravel their secrets. So buckle up. By the end of this journey, you'll never look at the night sky the same way again. At the heart of every black hole lies a mystery so profound it bends the rules of physics, a singularity. Picture taking the entire mass of a star, something millions of times larger than Earth, and crushing it down into an infinitely small point. That's what happens in the core of a black hole. Gravity wins, matter loses. The result, a place where density becomes infinite, where the very concept of space breaks down. This isn't just extreme gravity, it's gravity with no limits. The pull is so strong that not even light, the fastest thing in the universe, can fight its way free. That's why we call it the event horizon, the point of no return. Once something crosses that boundary, it's gone forever, stretched and squeezed in ways we can barely comprehend. But here's what's even wilder: the singularity itself. Infinite density means all the matter that ever fell into the black hole gets compressed into a space smaller than an atom. The equations of general relativity tell us this should happen, but our understanding of physics simply can't handle infinity. It's like dividing by zero, the math screams in protest. That's why scientists suspect a deeper theory, something beyond Einstein's work, must be waiting to explain what truly happens in that unknowable darkness. And yet, despite the chaos at its core, a black hole's influence is eerily simple. From the outside, it's defined by just 3 things: mass, spin, and charge. Everything else, every star, every planet, every unlucky spaceship that ever crossed its path gets erased, leaving no trace behind. It's almost poetic in its brutality. A cosmic shredder, reducing the universe's complexity to its most basic elements. So what does this mean for us? If you ever found yourself near a singularity, time itself would warp in impossible ways. A minute for you could be centuries for someone far away. The forces would stretch your body into a strand of atoms, a process scientists grimly call spaghettification. But beyond the nightmare fuel, black holes challenge us to think bigger. They're proof that the universe holds extremes beyond imagination, places where the laws we take for granted simply stop. And maybe, just maybe, hidden in that infinite density, lies the key to unlocking the next great revolution in physics. If black holes represent gravity's ultimate victory, neutron stars are its most brutal display of cosmic craftsmanship. These remnants of massive stars that went supernova pack so much mass into such a small space that the numbers stop making sense. Take our Sun, 1 million Earths could fit inside it. Now crush that entire star down to the size of Manhattan. That's a neutron star. The density here is beyond anything we experience on Earth. A single teaspoon of neutron star material would weigh about 1 billion tons, as much as Mount Everest. Picture trying to lift a mountain with a teaspoon. Impossible, right? That's the reality of matter compressed to its absolute limit, where atoms themselves collapse. Protons and electrons get smashed together so violently they fuse into neutrons, creating an ocean of pure nuclear material with no empty space left. What's even more astonishing is how this extreme density warps space around it. The gravity on a neutron star's surface is about 100 billion times stronger than Earth. If you dropped an object from just 1 meter above the surface, it would hit the ground at nearly 7% the speed of light. That kind of acceleration would turn any ordinary material into plasma instantly. Yet despite their crushing gravity, neutron stars aren't just inert balls of doom. Some spin hundreds of times per second, whipping around so fast their surfaces move at a significant fraction of light speed. These pulsars send out beams of radiation that sweep across space like cosmic lighthouses, creating some of the most precise clocks in the universe. Others, called magnetars, have magnetic fields so intense they could erase your credit card from halfway across the Milky Way. These stars aren't just curiosities, they're natural laboratories testing the limits of physics. The matter inside them exists in states we can't recreate on Earth, where the very rules of quantum mechanics get stretched to breaking point. Some theories suggest that deep in their cores, neutrons themselves might break down into a soup of even more fundamental particles, creating exotic states of matter that could rewrite our understanding of nuclear physics. And here's the real kicker: neutron stars might be the universe's ultimate alchemists. When two of them collide, the incredible pressures can forge heavy elements like gold and platinum in seconds, scattering them across space. That wedding ring on your finger, the gold in it was probably created in a neutron star collision billions of years ago. So while these celestial powerhouses might seem like cosmic oddities, they're actually key players in creating the very building blocks of planets. And life itself. Einstein's theory of relativity revealed something astonishing: gravity doesn't just bend space, it bends time itself. And nowhere is this effect more extreme than near a supermassive black hole, where the gravitational pull is so immense that time slows to a crawl. Imagine two identical clocks, one placed near Earth's surface ticking away normally, and another hovering just outside a black hole's event horizon. Over the course of a few hours, Earth's clock might count thousands of seconds while the black hole's clock barely moves. This isn't science fiction. It's a real phenomenon called gravitational time dilation, where the stronger the gravity, the slower time flows. An astronaut orbiting close to a black hole might experience just a few minutes, while decades or even centuries could pass for everyone else in the universe. The reason: gravity warps space-time so severely that it stretches the very fabric of time, like a weight pressing down on a trampoline. The deeper the dent, the slower time runs for anyone caught in it. Think about what this means for someone unlucky enough to fall toward a black hole. From their perspective, time feels normal, but from the outside, they'd appear to freeze in place, their movements slowing to an infinite crawl as they approach the event horizon. Light from them would redshift into oblivion, stretching into wavelengths we can't even see. It's like watching a movie stuck in slow motion, only the film never reaches the next frame. But here's the real twist: this isn't just a black hole quirk. Earth's gravity does this too, just on a much smaller scale. GPS satellites have to account for time dilation because their clocks tick faster in orbit than on the ground, by about 1 second every 30,000 years. If engineers ignored this effect, your phone's navigation would be off by miles within minutes. Black holes take this to the extreme, turning time dilation into a cosmic spectacle. Some supermassive black holes, like the one at the center of our galaxy, have gravity so strong that a single orbit around them could mean centuries pass elsewhere. It's a mind-bending reminder that time isn't the rigid, universal constant we think it is. It's fluid, stretched and warped by gravity like taffy, proving that even something as fundamental as the passage of time bends to the universe's most extreme forces. In 1915, Einstein predicted something extraordinary: that the universe isn't just space filled with stars and planets, but a dynamic fabric that can stretch, warp, and even ripple like the surface of a pond. Fast forward a century, and scientists proved him right in the most spectacular way possible. On September 14, 2015, a pair of observatories called LIGO caught the faintest whisper from a billion light-years away, a gravitational wave. This wasn't just any ripple in space-time. It was the aftermath of two black holes, each about 30 times the mass of our Sun, spiraling toward each other at half the speed of light before colliding in a cataclysmic merger. In that final millisecond, they released more energy than all the stars in the observable universe combined, energy that surged outward as gravitational waves, stretching and squeezing space-time itself as they traveled. Imagine dropping two pebbles into a still pond. The ripples spread outward, making the water rise and fall in gentle waves. Now replace the pond with the fabric of reality, and the pebbles with black holes moving at relativistic speeds. The result, space-time itself flexing, passing through planets, stars, and even you as it travels, though the effect is so tiny you'd never feel it. That's what makes LIGO detection so mind-blowing. Their instruments measured distortions 10,000 times smaller than a proton. To put that in perspective, it's like detecting a change in the distance to the nearest star that's less than the width of a human hair. And that signal, it matched Einstein's predictions perfectly, confirming gravitational waves after a century of speculation. But here's what's even wilder: this wasn't a one-time event. Since that first detection, LIGO and its European counterpart, Virgo, have caught dozens of these cosmic tremors. Some come from black holes merging in the darkest corners of the universe. Others originate from neutron stars colliding, events so violent they forge gold and platinum in their wake. Each wave is like a cosmic telegram, carrying secrets about the most extreme objects in existence. What's next? Scientists are already building more sensitive detectors, like the future space-based LISA mission, which could catch waves from supermassive black holes merging at the dawn of time. These ripples aren't just curiosities, they're an entirely new way to hear the universe, revealing hidden chapters of cosmic history we've never been able to read before. And this is just the beginning. If black holes are cosmic vacuum cleaners, sucking everything in with no escape, then white holes are their theoretical opposite: cosmic fire hydrants blasting matter and energy outward with unstoppable force. Picture a black hole running in reverse, where the event horizon becomes an impenetrable barrier nothing can cross from the outside. Not even light could enter. Instead of crushing matter into oblivion, a white hole would violently expel it, spewing out everything it contains in a fiery torrent that defies gravity's pull. The math of general relativity actually allows for white holes to exist. Einstein's equations are symmetrical, meaning they work just as well backward as forward. Flip a black hole's behavior in time, and you get a white hole. Some physicists speculate that if you could peer inside a black hole's singularity, you might find it connected to a white hole in another universe, a one-way tunnel through space-time called an Einstein-Rosen bridge, or more poetically, a wormhole. But here's the catch: while black holes form naturally from collapsing stars, white holes would require some bizarre cosmic birth. They couldn't arise from normal astrophysical processes. Instead, they'd need to pop into existence fully formed, already packed with matter and energy to eject. And once they started erupting, they'd have to somehow resist collapsing back into a black hole under their own gravity, a bit like trying to keep an exploding firework from ever coming back down. That's why most scientists think white holes are mathematical curiosities rather than real objects. The universe tends to favor processes that increase entropy or disorder, and white holes seem to defy that principle by appearing impossibly organized. Yet there's one tantalizing possibility. Some theorists suggest the Big Bang itself could have been a white hole event, with our entire universe erupting from a singularity in an explosive, time-reversed version of black hole physics. The most compelling argument against white holes: we've never seen one. No astronomical observation has ever detected an object that perfectly matches their predicted behavior. But absence of evidence isn't evidence of absence, especially when we're dealing with something so strange. If white holes do exist, they might be fleeting, vanishing in a flash of energy before we can spot them. Or they could be hiding in plain sight, masquerading as other cosmic phenomena like gamma-ray bursts or quasars. So why keep searching? Because white holes push our understanding of physics to its limits. They force us to grapple with questions about time's arrow, the nature of singularities, and whether the universe might have hidden dimensions or parallel realities. Even if they don't exist, the mere possibility challenges us to think bigger, to imagine a cosmos where gravity's extremes aren't just destructive but creative, hurling new worlds into existence instead of swallowing them whole. And in that sense, whether real or hypothetical, white holes remind us that the universe's mysteries are far from solved. The sun might seem like just a bright light in our sky, but its gravity is powerful enough to bend the very fabric of reality. This isn't an exaggeration, it's a proven phenomenon called gravitational lensing, and it was one of Einstein's boldest predictions. Picture this: in 1919, during a total solar eclipse, scientists pointed their telescopes at stars near the sun's edge. Normally, those stars would be hidden by the sun's glare, but something remarkable happened. The stars appeared slightly out of place, as if their light had taken a detour around the sun before reaching Earth. Einstein had predicted this exact effect. His theory of general relativity stated that massive objects like the sun warp spacetime, creating a sort of cosmic trampoline. When light from distant stars passes close to the sun, it doesn't travel in a straight line. It follows the curve of this warped space, bending around the sun like a marble rolling along a dip in a rubber sheet. The result: the stars looked shifted from their true positions, even though their light was just taking a gravity-altered shortcut through space. This was no small discovery. That eclipse observation became the first direct proof of Einstein's theory, catapulting him to worldwide fame. But here's what's even more incredible: gravitational lensing isn't unique to our sun. Any massive object can do it. Galaxies, black holes, even galaxy clusters act as cosmic magnifying glasses, warping and amplifying the light of objects behind them. Sometimes this creates bizarre optical illusions, like duplicate images of the same distant quasar, or stretched out arcs of light resembling celestial smudges. But gravitational lensing isn't just a cool trick. It's one of astronomy's most powerful tools. By measuring how much light bends, scientists can map invisible dark matter, which doesn't emit light but still warps spacetime with its gravity. They've even used lensing to spot some of the universe's earliest galaxies. Their light bent and magnified by foreground galaxy clusters like a natural telescope. And here's the kicker: without the sun's gravity bending starlight during that eclipse over a century ago, we might never have confirmed Einstein's radical ideas. That single observation reshaped our understanding of gravity, proving it wasn't just a force but a curvature of spacetime itself. So the next time you feel the sun's warmth, remember, its gravity is doing far more than keeping Earth in orbit. It's twisting the very path of light, revealing hidden truths about the cosmos. We think of black holes as cosmic anchors, monsters lurking at the centers of galaxies, holding everything in their gravitational grip. But what if I told you some black holes are anything but stationary? Imagine a behemoth with the mass of 20 suns, hurled through space at millions of miles per hour, invisible and undetectable until it's too late. These aren't theoretical nightmares, they're rogue black holes, and they're roaming the galaxy right now. Here's how it happens. When two galaxies collide, their central supermassive black holes eventually spiral toward each other, locked in a deadly dance. As they merge, the energy released can kick the resulting black hole clear out of the galaxy like a cosmic slingshot. But smaller black holes don't need galactic collisions to go rogue. A single supernova explosion can send its remnant black hole careening into the void at staggering speeds. The terrifying part, these wanderers are nearly impossible to spot. Unlike active black holes that devour gas and glow with X-rays, rogue black holes drift through the cold emptiness of space, betraying their presence only through subtle gravitational tricks. Astronomers hunt them by watching for stars that mysteriously flicker or wobble, telltale signs of an invisible predator warping space-time around them. One candidate, detected in 2011, might be a rogue black hole 7 times the mass of our Sun, drifting just 3,000 light-years away. If it passed through our solar system, an extremely unlikely but chilling scenario, its gravity could fling planets out of orbit like marbles before we even knew it was there. Yet rogue black holes aren't just destructive, they're cosmic time capsules. Some may be primordial black holes, forged in the chaos of the Big Bang itself, carrying secrets about the universe's earliest moments. Others might be coated in dark matter, acting as invisible probes of this mysterious substance. And if Hawking radiation is real, these solitary wanderers could be slowly evaporating, their final moments emitting bursts of particles that reveal quantum gravity's deepest truths. So while they might sound like science fiction, rogue black holes are a reminder of how dynamic and unpredictable our universe really is. They prove that even the most extreme gravitational forces aren't always where we expect them to be. Sometimes the deadliest things in the cosmos are the ones we can't see coming. Gravity's grip isn't always uniform. Sometimes it pulls harder on one side of an object than the other, creating forces so violent they can turn planets, stars, and even hypothetical astronauts into cosmic spaghetti. This nightmare scenario has a name: spaghettification. Picture yourself falling feet first toward a black hole. The gravitational pull on your toes would be exponentially stronger than on your head, stretching your body into a thin strand of atoms like taffy in an invisible candy machine. It sounds like horror fiction, but this exact process has been witnessed in real time, not with humans, but with unfortunate stars that wandered too close to these cosmic shredders. Take the event spotted in 2019, when astronomers watched as a black hole 25 million times the Sun's mass tore apart a star in a galaxy 750 million light-years away. As the star crossed the black hole's tidal radius, the point where gravity's differential force overcomes the star's own gravity, it was stretched into a glowing streamer of plasma. Over weeks, this noodle of stellar material wrapped around the black hole in a swirling disk, heating up to millions of degrees and emitting X-rays visible across the universe. The phenomenon, poetically named a tidal disruption event, is one of the most violent demonstrations of gravity's power to distort reality. But why does this happen? It all comes down to the inverse square law. Gravity weakens with distance, but near a compact object like a black hole or neutron star, the difference in pull between your head and feet becomes extreme. Near Earth, this effect is negligible. Our planet's gravity barely changes between your height and the ground, but near a black hole just 60 miles wide, the difference could be thousands of times stronger at your feet, stretching you like a rubber band until molecules tear apart. Even steel would behave like soft putty under these conditions. The universe offers even stranger examples. Neutron stars, with their insane surface gravity, can create tidal forces strong enough to strip gas from companion stars in razor-thin streams. In binary systems like Hercules X1, astronomers see this process in action, a neutron star siphoning material from its neighbor, the stolen gas spiraling inward at nearly light speed before slamming into the star's surface in bursts of X-rays. Here's the chilling takeaway: spaghettification isn't some abstract extreme. It's a fundamental consequence of gravity's nature, playing out constantly across the cosmos. Every tidal disruption event, every stretched star, is a reminder that the universe has no regard for the integrity of matter when gravity decides to flex its full power. And in those final moments before being shredded, even a star, a massive ball of plasma that once shone for billions of years, becomes nothing more than a flickering strand of light, bending to the will of spacetime's most unforgiving forces. Hidden in the depths of intergalactic space, something massive is pulling us toward oblivion at 14 million miles per hour, and no one knows exactly what it is. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it yanks entire galaxy clusters, including our own Milky Way, through the cosmic void like leaves caught in a hurricane. For decades, this invisible force remained one of astronomy's greatest enigmas, buried behind the thick dust of our galaxy's central plane where telescopes couldn't peer. The story begins in the 1970s when scientists noticed something bizarre. Every galaxy in our local supercluster was streaming toward the same patch of sky near the constellation Centaurus. This wasn't just random motion, it was a coordinated cosmic march, as if some unseen hand were herding galaxies across the universe. The culprit, a gravitational pull equivalent to tens of thousands of Milky Ways concentrated in a region just 300 million light-years away. But here's the twist: we shouldn't be moving that fast. Based on the distribution of visible matter, the pull isn't strong enough to explain our breakneck velocity. That means something massive, something we can't see, is lurking there. At first, astronomers thought it might be a colossal cluster of galaxies, but even that didn't account for the numbers. Then came a shocking realization: the Great Attractor isn't the final destination. It's just a waypoint on a far larger journey. Recent observations reveal we're not just falling toward the Great Attractor. We, along with thousands of other galaxies, are being dragged toward something even more enormous: the Shapley supercluster, the most massive concentration of matter in the observable universe. A staggering 650 million light-years away, Shapley's gravity is like a cosmic whirlpool, pulling in everything around it, including the Great Attractor itself. Yet mysteries remain. Why is the pull stronger than visible matter can explain? Some suspect hidden filaments of dark matter, weaving through space like invisible scaffolding, amplifying gravity's grip. Others propose vast, undiscovered galaxy clusters obscured by interstellar dust. One thing's certain: this relentless motion isn't just a curiosity. It's proof that our cosmic neighborhood is far more dynamic than we ever imagined. So what happens when we get there? Don't panic. The Milky Way won't crash into anything. The expansion of space ensures we'll never actually reach the Great Attractor or Shapley. Instead, we're caught in an endless cosmic river flowing toward an unseen horizon, reminding us that even on the grandest scales, gravity is still full of surprises. And somewhere out there, in the darkness between the stars, the universe's greatest tug-of-war continues, hidden in plain sight. Einstein's theory of relativity explains the universe on grand scales: black holes bending space-time, galaxies warping light, while quantum mechanics rules the subatomic world, where particles pop in and out of existence in a probabilistic dance. Yet when these two titans of physics collide, the result isn't harmony, it's chaos. Black holes shouldn't be able to exist according to quantum rules. Particles shouldn't behave so unpredictably near a singularity. The math simply breaks down. This isn't just a gap in our knowledge, it's a chasm, one that physicists have spent decades trying to bridge with a single, elegant solution: quantum gravity. The challenge: gravity is laughably weak compared to the other fundamental forces. A tiny magnet can lift a paperclip, overcoming Earth's entire gravitational pull. But in extreme environments like the center of a black hole or the first moments of the Big Bang, gravity becomes the dominant force, squeezing matter into volumes so small that quantum effects can't be ignored. Here, the smooth fabric of relativity shatters into a froth of uncertainty, where space-time itself might be pixelated, vibrating, or even emerge from something deeper. Two leading theories attempt to reconcile this divide: string theory and loop quantum gravity. String theory proposes that particles aren't dots but tiny, vibrating strings, with different vibrations producing different forces and matter. In this framework, gravity isn't special, it's just another note in the cosmic symphony, unified with the other forces at energies so high they haven't existed since the universe's first trillionth of a second. But string theory demands extra dimensions, 6 or 7 of them, curled up so tightly we'd never notice. Loop quantum gravity takes a dramatically different approach. Instead of strings, it imagines spacetime as a network of interconnected loops, like an unimaginably fine mesh. At the smallest scales, this mesh prevents matter from collapsing into singularities by creating a sort of quantum repulsion, a last-ditch barrier against infinite density. It's a compelling idea, but one that struggles to explain how smooth spacetime emerges from this chaotic web. Yet the real test of any quantum gravity theory isn't elegance, it's evidence. And here's where things get thorny. The energy required to probe these scales is beyond anything we can produce, even in particle colliders like the Large Hadron Collider. So scientists look for indirect clues, subtle anomalies in cosmic microwave background radiation, unexpected patterns in gravitational waves, or even hints from black hole thermodynamics. Some speculate that when black holes evaporate via Hawking radiation, they might leave behind quantum footprints, tiny deviations from classical predictions that could point toward a deeper theory. The stakes couldn't be higher. Unifying these frameworks wouldn't just tidy up physics, it could rewrite our understanding of reality's fabric, revealing whether time truly flows, if wormholes are possible, or why the universe exists at all. For now, quantum gravity remains the ultimate puzzle, a frontier where the very rules of existence are waiting to be decoded. And when that breakthrough comes, it won't just explain black holes or the Big Bang, it might finally answer what spacetime truly is. Black holes don't always come in supermassive or stellar-sized packages. Some could be smaller than an atom, yet denser than a mountain. These hypothetical objects, known as primordial black holes, might have formed in the chaotic furnace of the early universe, mere fractions of a second after the Big Bang. Unlike the black holes we're familiar with, which arise from collapsing stars, these tiny terrors wouldn't need a star's death to exist. Instead, they'd be cosmic relics, born from the intense pressures of the newborn universe, where fluctuations in density could have packed matter tightly enough to collapse into microscopic singularities. The wildest part, some theories suggest these minuscule monsters could still be lurking around today, maybe even in our own solar system. Picture a black hole with the mass of an asteroid, compressed into a space smaller than a proton. Its gravity would be strong enough to bend light, yet its event horizon would be so tiny it could pass through matter almost unnoticed, like a ghost slipping through walls. If one orbited the Sun, we might never know unless it betrayed its presence by tugging on nearby objects or emitting a faint whisper of Hawking radiation. The theoretical particles black holes are thought to emit as they slowly evaporate. But why should we care about something so small? Primordial black holes could solve some of astronomy's biggest mysteries. For decades, scientists have puzzled over dark matter, the invisible substance making up most of the universe's mass. While most theories point to exotic particles, some researchers propose these tiny black holes could be the missing ingredient. If enough of them formed in the early universe, they might collectively account for dark matter's gravitational effects hiding in plain sight all this time. There's another tantalizing possibility. Some primordial black holes might not be so primordial. High-energy collisions in particle accelerators or even cosmic ray impacts could theoretically create microscopic black holes under certain conditions. These wouldn't last long. They'd evaporate in a flash due to their tiny size, but their fleeting existence would prove that black holes aren't just stellar-scale phenomena. They could form anywhere, anytime, given the right extremes of energy and density. Of course, finding one is another story. Detecting a black hole the size of a speck of dust would require technology we don't yet have. Some proposals involve looking for telltale flashes of gamma rays, the final bursts of energy as they evaporate, or monitoring stars for subtle flickers caused by invisible objects passing in front of them. Others suggest watching for bizarre gravitational lensing effects on distant starlight, where a tiny but massive object warps light in ways nothing else could. Whether they exist or not, primordial black holes push our understanding of gravity to its limits. They force us to ask, how small can a black hole be? Can gravity truly overpower quantum forces at such infinitesimal scales? And if these ghostly remnants of the early universe are real, what else might be hiding in the cosmic shadows, waiting to rewrite the rules we thought we knew? Gravity may shape galaxies and crush stars into black holes, but here's a cosmic irony. It's actually the weakest of nature's fundamental forces by a staggering margin. Hold a fridge magnet near a metal surface and watch it stick effortlessly. That tiny magnet's electromagnetic force just defeated the gravitational pull of our entire planet. To put numbers to it, gravity is about 10 to the 39th power times weaker than electromagnetism. That's a 1 followed by 39 zeros. If gravity were a whisper, electromagnetism would be a supernova. So why does gravity dominate the cosmos while the other forces seem like background players? The secret lies in two factors: range and buildup. Electromagnetism and nuclear forces have limited reach or cancel themselves out. Positive and negative charges neutralize. Quarks bind tightly inside atoms. But gravity has no off switch. It only pulls, never pushes, and its influence stretches infinitely through space. Over vast distances, while other forces fade into irrelevance, gravity keeps stacking its effects. A single star's pull might be weak, but a galaxy's worth of stars, that's enough to bend light and trap spacetime itself. Consider a neutron star's surface, where gravity is so strong it warps atoms into spaghetti. Yet even there, if you could scrape off a speck of material, its electromagnetic forces would overpower gravity's grip, flinging particles apart violently. Gravity only wins when you gather enough mass in one place, like packing a sun's worth of material into a city-sized sphere. That's why black holes are the ultimate gravity champions. They compress so much mass into such tiny volumes that not even light speed can escape their pull. Here's where things get really weird. At the quantum scale, gravity barely registers. Particles in accelerators zip around, their movements dictated by electromagnetism and nuclear forces, while gravity's influence is too feeble to measure. Scientists still don't know why there's such a colossal gap between gravity's weakness and the other forces' strength, a mystery called the hierarchy problem. Some theories suggest extra dimensions could be diluting gravity, or that undiscovered particles might bridge the divide. Yet gravity's weakness is also its superpower. Because it doesn't cancel out, it sculpts the universe's large-scale structure, weaving galaxies into vast cosmic webs. Without it, planets wouldn't orbit, stars wouldn't ignite, and life as we know it wouldn't exist. So while a magnet can defy Earth's gravity, it's gravity's quiet persistence, its infinite patience that holds the cosmos together. And in that paradox lies one of nature's most elegant balancing acts. The weakest force builds the grandest structures. In the darkest corners of the cosmos, some black holes don't just lurk silently, they erupt in explosions of energy so intense they outshine a trillion suns. These aren't ordinary black holes, they're supermassive beasts millions to billions of times heavier than our sun, and when they feed, they become the brightest objects in the universe, quasars. Back in the 1960s, astronomers first spotted these brilliant points of light and assumed they were nearby stars until they checked the math. The light from quasars wasn't just bright, it was coming from billions of light years away, meaning these objects were emitting more energy than entire galaxies packed with hundreds of billions of stars. How? The answer lies in the chaos of supermassive black holes gone wild. Picture a black hole with the mass of a billion suns, surrounded by a swirling disk of superheated gas and dust. As material spirals inward, friction heats it to millions of degrees, turning it into a glowing maelstrom of plasma. But here's where the magic happens: not all that material falls in. Some gets channeled by the black hole's insane magnetic fields into jets of particles shooting outward at nearly light speed. These jets, stretching hundreds of thousands of light years into space, act like cosmic blowtorches, lighting up intergalactic gas like a neon sign in the void. What makes quasars truly mind-bending is their efficiency. A typical quasar converts about 10% of its infalling mass directly into energy. Compare that to a star like our Sun, which turns less than 1% of its mass into energy over its entire lifetime. That's why a single quasar can outshine an entire galaxy while occupying a space smaller than our solar system. Yet quasars aren't just relics of the past. They're cosmic signposts marking a violent phase in galactic evolution. Most massive galaxies, including our own Milky Way, likely hosted a quasar in their youth when their central black holes were still feasting on the gas-rich chaos of the early universe. Today, many of those black holes have gone quiet, their fuel exhausted. But occasionally, even modern galaxies like ours can flicker back to life if fresh gas drifts too close to the sleeping giant at their core. The most luminous quasar ever discovered, J0159 plus 0655, beams light from a time when the universe was barely 700 million years old. Its black hole weighs in at over 16 billion solar masses, a baffling size for such an early era, forcing scientists to rethink how these monsters grow so fast. Some theories suggest they form from direct collapse of primordial gas clouds, skipping the star stage entirely. Others propose they gorged themselves during chaotic galactic mergers, where torrents of gas funneled into their waiting gravitational maws. Quasars do more than dazzle, they shape their surroundings. Their intense radiation can blast gas out of galaxies, shutting off star formation and leaving behind red and dead galactic husks. Their jets carve bubbles in intergalactic space, influencing where new galaxies can form. And ironically, by pushing gas away, they might also regulate their own growth, preventing their black holes from becoming too massive too quickly. What's wildest, we're seeing these objects as they were billions of years ago, their light only now reaching us. Many quasars have likely burned out by now, their black holes starved into silence. But their light still travels across the cosmos, carrying snapshots of a younger, more violent universe, one where gravity's most extreme forces weren't just destructive but creative, forging the galaxies we see today. And somewhere out there, new quasars may be waking up, ready to ignite the darkness once more. What if everything we think we know about gravity is just an illusion? Some of the most radical theories in physics suggest that gravity might not be a fundamental force at all, but rather a side effect, a cosmic mirage emerging from deeper laws we haven't yet uncovered. One of these mind-bending ideas is called emergent gravity, and it turns our understanding of the universe on its head. The concept comes from theoretical physicist Eric Verland, who proposed that gravity isn't something woven into the fabric of space-time, but instead arises from something far more abstract: information. Imagine the universe as a vast, interconnected network where every particle, every star, and every black hole is constantly exchanging tiny bits of data. According to this theory, gravity emerges from the way this information reorganizes itself, like the way heat isn't a thing but a byproduct of moving molecules. Here's where it gets even stranger. Verlon's math suggests that gravity might be linked to entropy, the measure of disorder in a system. Think of entropy like the universe's need to spread things out. Ice melts, coffee cools, galaxies disperse. What if gravity is just nature's way of shuffling cosmic information to maximize entropy? In this view, the force we feel keeping us grounded isn't a pull between masses but a statistical tendency for the universe to arrange itself in the most probable way. But why consider such a wild idea? Because it could solve one of physics' greatest puzzles, dark matter. Astronomers know galaxies rotate faster than they should based on visible mass alone, so they invented dark matter to explain the discrepancy. Emergent gravity eliminates the need for it. The math predicts galaxy rotations perfectly without invoking invisible particles, just by recalculating how gravity emerges from entropy on cosmic scales. Not everyone's convinced. Critics argue emergent gravity struggles to explain phenomena like gravitational waves or the bending of light around galaxies. And without experimental proof, it remains a fascinating thought experiment rather than law. Yet the theory forces us to ask profound questions. Is gravity truly fundamental or just a shadow of deeper physics? Could the other forces, electromagnetism, the nuclear forces, also be emergent, leaving us with a universe where nothing is as it seems? For now, Einstein's relativity still reigns supreme. But history shows science advances when we question the obvious. After all, Newton's gravity seemed perfect until Einstein showed it was incomplete. Maybe one day we'll look back and realize gravity was never a force at all, just the universe's way of keeping track of itself. Gravity may be the force that binds galaxies together, but there's something else out there, an invisible, mysterious power working against it, stretching the very fabric of space faster than gravity can keep up. We call this force dark energy, and its discovery in the late 1990s shook astronomy to its core. Before then, scientists assumed the universe's expansion, set in motion by the Big Bang, would eventually slow down thanks to gravity's relentless pull. But when they measured distant supernova, they found the opposite. The universe wasn't just expanding, it was accelerating, as if some unseen hand were pressing down on cosmic scales, pushing galaxies apart at an ever-increasing rate. The implications are staggering. Dark energy isn't just countering gravity, it's dominating it, making up roughly 68% of the universe's total energy content. To put that in perspective, all the stars, planets, black holes, and galaxies we can see account for less than 5% of the cosmos. Dark energy is the heavyweight champion, an anti-gravity force woven into space itself. And unlike gravity, which weakens with distance, dark energy's repulsive effect grows stronger as the universe expands, creating a runaway effect with no end in sight. This leads to a chilling cosmic prophecy. In tens of billions of years, galaxies beyond our local group will be so far away that their light will no longer reach us. The universe will grow cold and lonely, with island galaxies drifting apart in an ever-darkening void. Eventually, even the closest neighbors will vanish beyond an unreachable horizon, their light stretched into wavelengths too faint to detect. Civilizations born in that distant era might look up at an empty sky, unaware that a vast cosmos once existed beyond their own isolated galaxy. Yet dark energy isn't just a cosmic destroyer, it's also a tantalizing puzzle. Some theories suggest it's the cosmological constant Einstein once proposed and later discarded, a property of empty space itself that gives it a kind of tension, like a stretched rubber sheet trying to snap back. Others speculate it could be a dynamic field, changing over time like an invisible fifth force of nature. The truth is, we don't know. What we do know is that dark energy's grip is tightening. Here's the real kicker. If dark energy's strength increases, it could eventually tear apart everything. Not just galaxies, not just stars, but atoms themselves in a catastrophic event called the Big Rip. It's an unlikely but sobering reminder that the universe's fate hinges on forces we're only beginning to understand. For now, gravity keeps our galaxy intact, our solar system stable, our feet on the ground. But out there, in the vast darkness between the stars, an invisible battle rages, one that gravity, for all its might, may ultimately lose. Imagine two black holes locked in a cosmic ballet, each so massive that their gravity bends the universe around them. Now picture them spiraling closer, circling one another at a fraction of light speed, their orbits tightening with each pass. This isn't just a slow dance, it's a death spiral, and the universe keeps the beat through ripples in spacetime itself. Here's how the end begins. When two black holes orbit each other, they don't move through empty space. They plow through the fabric of reality, sending out gravitational waves like a boat churning through water. These waves carry energy away from the system, causing the black holes to lose speed an inch closer together. At first, it's imperceptibly slow, a few meters over centuries. But as the distance shrinks, the waves intensify, draining energy faster and accelerating the inevitable. By the final moments, the black holes whip around each other hundreds of times per second, warping spacetime so violently their gravitational waves can be detected across the cosmos. Then comes the collision. In the last millisecond, the two singularities merge, releasing more energy than all the stars in the observable universe combined in the form of pure gravity. The resulting shockwave distorts spacetime so profoundly that it briefly makes the entire cosmos ring like a bell. Scientists call this moment the ring down, where the newborn black hole wobbles like a drop of water before settling into a perfect sphere. But what's left behind? A single, more massive black hole, its surface area greater than the sum of its parents, a cosmic testament to the universe's strangest arithmetic. We know this happens because we've heard it. In 2015, LIGO detected gravitational waves from two black holes 30 times the Sun's mass colliding 1.3 billion light-years away. The signal matched Einstein's predictions perfectly. The rising chirp of their final orbits, the sudden thud of merger, then the fading ripple of the ring down. Since then, dozens of these events have been recorded, some involving black holes far heavier than theorists thought possible. One merger in 2019 created a black hole 142 times the Sun's mass, the first solid evidence for the elusive intermediate mass black holes. But the most thrilling part, these dueling black holes can form in wildly different ways. Some might be born together from twin stars that both collapsed. Others could meet later in life, trapped in crowded galactic cores where gravity shoves them into fatal embraces. A few might even be primordial black holes, ancient relics from the Big Bang era that finally found a partner after eons alone. Each merger tells a story. The spin of the final black hole reveals whether the original pair orbited in sync or clashed at odd angles. The frequency of the waves betrays their masses. Even the volume of the signal hints at how far away they were when the universe was younger. These collisions aren't just violent in points, they're cosmic broadcasts, echoing secrets about how black holes live, move, and shape the galaxies around them. And with every new detection, we're tuning into a darker, more dynamic universe than we ever imagined. You might think gravity is the same everywhere on Earth after all. It's what keeps us all firmly planted on the ground. But here's a strange truth. Our planet's gravitational pull isn't uniform. Step into certain regions and you'll weigh slightly less without shedding a single pound. One of the most baffling spots, Canada's Hudson Bay, where gravity is measurably weaker than anywhere else on the planet. This anomaly isn't some glitch in the universe's code. It's the result of two fascinating geological phenomena working in tandem. First, imagine the colossal weight of ice sheets 2 miles thick. pressing down on the Earth's surface during the last ice age. That ice was so heavy it literally deformed the planet, pushing the crust downward like a finger pressing into memory foam. When those glaciers melted 12,000 years ago, the land began slowly rebounding, but it hasn't fully bounced back yet. That missing mass means less gravitational pull in the region, like removing weights from a scale. But there's another player beneath the surface: convection currents in Earth's mantle. Our planet isn't just a solid rock, it's a dynamic system where molten rock circulates slowly over millions of years, dragging tectonic plates along like a conveyor belt. Beneath Hudson Bay, these currents are pulling material away from the area, creating a subtle but measurable dip in the density of the underlying rock. Less mass equals weaker gravity, making this one of the lightest spots on Earth in more ways than one. Satellites like Grace Gravity Recovery and Climate Experiment have mapped these variations with stunning precision, revealing a patchwork of gravitational highs and lows across the globe. Mountain ranges like the Himalayas create stronger gravity because of their sheer mass, while deep ocean trenches have slightly weaker pulls. Even changes in groundwater or melting ice caps can shift local gravity over time, proving Earth's gravitational field is far from static. So how much lighter would you feel in Hudson Bay? Don't expect to float away. The difference amounts to about 1/400%. That's roughly the weight of a penny less for every 200 pounds. But here's what's wild. This isn't just a quirky Earth fact. Similar variations exist on other worlds. Mars's Tharsis volcanoes create gravitational spikes, while Jupiter's moon Io has tides so strong they reshape the moon itself. Gravity isn't just a force, it's a fingerprint, revealing the hidden dynamics of planets and stars. Next time you stand on solid ground, remember, the pull you feel isn't just Earth's, it's your specific spot's gravity, shaped by ice ages, molten rock, and forces deeper than we can see. And somewhere in Canada, right now, the ground is still rising millimeter by millimeter, waiting for gravity to catch up. The universe we see, with its 3 dimensions of space and 1 of time, might be just the surface of something far stranger. Some physicists suspect gravity's puzzling weakness compared to other forces could have a radical explanation. It's not confined to our reality. Unlike electromagnetism or nuclear forces, which lock particles tightly together, gravity could be leaking into hidden dimensions beyond our perception, diluting its strength in our visible universe like water seeping through cracks in a dam. This isn't just wild speculation, it's a core idea in string theory, which proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings. For the math to work, these strings need more space to vibrate than our familiar 3 dimensions. They require at least 6 extra dimensions, curled up so tightly that even atoms seem vast by comparison. In this framework, gravity's strings might reach into these hidden dimensions, explaining why its pull feels so feeble compared to forces stuck in 3D. Imagine blowing smoke across a window screen. Most smoke particles collide with the screen, staying trapped on one side like electromagnetism's influence. But a few slip through the gaps, vanishing into the open air beyond. If gravity behaves like those escaping particles, it would appear weaker on our side of reality simply because some of its influence is bleeding elsewhere. The Large Hadron Collider briefly fueled hopes of detecting these extra dimensions. Scientists theorized that if 2 particles collided with enough energy, they might eject a graviton, the hypothetical particle carrying gravity into another dimension, leaving behind a telltale missing energy signature. So far, no luck, but other experiments are hunting for deviations in gravity's strength at microscopic scales, where extra dimensions effects might become noticeable. Even the motion of planets could hold clues. Tiny anomalies in their orbits might betray the gravitational tug of unseen dimensions warping space nearby. Not everyone's convinced. Critics argue extra dimensions are an elegant math trick with no observational proof. Yet the puzzle remains: why is gravity so weak? If the answer truly lies in hidden dimensions, it would rewrite our understanding of reality's fabric, suggesting we're living on a cosmic membrane floating in a higher dimensional space. Every time you drop your keys, their fall might be governed not just by the gravity you feel, but by forces playing out in realms we can't even imagine. And here's the kicker: if gravity can leak out, what's stopping other forces or objects from slipping into these dimensions? Some theories suggest black holes might be portals to them, their singularities punching through spacetime like needles through fabric. Others propose that dark matter could be ordinary matter drifting in a parallel dimension, its gravity seeping into ours. Whatever the truth, one thing's certain: the cosmos has quirks we've barely begun to explore. And if gravity's hiding secrets in unseen dimensions, the universe is far stranger and vaster than we ever dreamed. Imagine a galaxy spinning so fast its stars should fling into the void, yet they don't. This cosmic mystery first struck astronomers in the 1930s when they clocked the motion of galaxies like Andromeda and found stars orbiting far quicker than visible matter could explain. The math was clear: there wasn't enough gravity from stars and gas to hold these galaxies together. Something invisible, something massive, was holding them in place with its gravitational grip. Today, we call that something dark matter, and its ghostly pull doesn't just anchor galaxies, it sculpts the universe's grandest structures. Dark matter's power lies in its silence. Unlike stars or gas, it doesn't emit, absorb, or reflect light. It's utterly transparent, detectable only through its gravitational handshake with visible matter. Picture a marble rolling around a bowl you can't see. You'd know the bowl exists by the marble's motion. That's how we map dark matter, by watching how it bends the paths of stars, distorts light from distant galaxies, and even warps the cosmic microwave background. The verdict: dark matter outweighs ordinary matter 5-to-1, weaving an invisible scaffold that galaxies cling to like dew on a spider's web. But dark matter isn't just cosmic glue, it's an architect. Simulations of the early universe reveal a startling truth: without dark matter's gravity, galaxies as we know them couldn't form. After the Big Bang, ordinary matter was too hot and energetic to clump together efficiently. Dark matter, unaffected by light or pressure, pooled first into vast halos, creating gravitational wells that funneled gas and stars into their grasp. Over billions of years, these halos merged and grew, birthing the galaxy clusters and superclusters we see today. The Milky Way, it's embedded in a dark matter halo 10 times more massive than all its visible stars combined. The evidence is everywhere. Take the Bullet Cluster, 2 galaxy clusters that collided head-on. When astronomers mapped their mass using gravitational lensing, they found a shocking disconnect. The visible gas, slowed by friction, lagged behind, while the bulk of the mass, guided by dark matter's ghostly presence, sailed ahead like a silent shadow. This cosmic snapshot proved dark matter isn't some theoretical crutch, it's a tangible, dynamic force that moves independently of the light-bound universe. Yet for all its influence, dark matter remains maddeningly elusive. Is it a sea of undiscovered particles, colder and slower than anything we've detected? Could it be primordial black holes forged in the universe's first second? Or does its mystery hint at something deeper, a flaw in our understanding of gravity itself? Whatever the answer, one thing's certain: the cosmos dances to the tune of an invisible maestro, and every galaxy, every star, every atom of our being moves in rhythm with its unseen hand. The faintest whisper from the dawn of time still echoes through the cosmos, a static hiss so quiet you'd miss it if you didn't know where to listen. This is the cosmic microwave background, the afterglow of the Big Bang, and buried within its subtle patterns lies a treasure trove of secrets about gravity's earliest moments. Picture the universe just 380,000 years after its violent birth, a searing plasma of particles and light so dense photons couldn't travel more than an atom's width before colliding. Then, in a flash, expansion thinned the soup enough for light to break free, creating the first snapshot of reality, a glow that's been cooling and stretching into microwaves over 13.8 billion years. But here's what's wild. That glow isn't perfectly uniform. Tiny temperature fluctuations, just 1 part in 100,000, paint a speckled tapestry across the sky. These imperfections are cosmic fossils, frozen ripples from an era when the universe was smaller than a grapefruit, and gravity was just beginning to flex its muscles. Some of those ripples may trace back to primordial gravitational waves, vibrations in space-time itself spawned during a hypothetical period called inflation, when the universe expanded faster than light in its first trillionth of a second. The smoking gun, a telltale swirl pattern in the microwave background's polarization called B modes, which some theories suggest could be the stretched signature of those ancient gravity waves. Detecting them would be like finding footprints in the ash of the Big Bang, proof that gravity was there at the very beginning, shaping the cosmos before atoms or stars even existed. In 2014, the BICEP 2 team thought they'd spotted this signal, only to realize interstellar dust had mudded the data. The hunt continues, with experiments like the Simons Array and future space telescopes scanning for cleaner traces of these space-time tremors. Why does this matter? Because inflation's gravity waves could reveal energy scales 1 trillion times beyond what particle colliders can probe, offering clues about how gravity interacts with quantum forces at conditions we'll never recreate. They might even hint at extra dimensions or a deeper theory unifying all physics. The cosmic microwave background isn't just a relic, it's a cipher, and gravity's fingerprints could be the key to decoding how everything began. And somewhere in that static, if we listen closely enough, the universe's first words might still be echoing. Most stars live quiet lives, orbiting their galaxies in predictable paths, but some are cosmic fugitives, hurled into the void at speeds so extreme they'll never return. These are hypervelocity stars, and their origins trace back to one of the universe's most violent matchups, a dance with a supermassive black hole. Picture a binary star system, 2 stars locked in mutual orbit, wandering too close to the monstrous black hole at a galaxy's center. The black hole's gravity grabs one star, yanking it into a fatal orbit, while the other gets slingshotted outward like a stone from a sling. The energy transfer is so brutal that the surviving star rockets away at over 1 million miles per hour, fast enough to escape its galaxy's gravitational pull entirely. It's the ultimate cosmic ejection, a stellar expulsion so forceful it defies the Milky Way's grip. The first hypervelocity star was discovered in 2005, a lone blue giant racing through intergalactic space at nearly 2.7 million miles per hour. Astronomers dubbed it HE 0437-5439, but its story was anything but clinical. This star wasn't just moving fast, it was on a one-way trip out of the Milky Way, destined to drift forever in the cold emptiness between galaxies. Since then, dozens more have been spotted, each with velocities that make our sun's sedate 490,000-mile-per-hour orbit seem glacial. But not all hypervelocity stars are born from black hole encounters. Some might be survivors of supernova explosions in tight binary systems, where the sudden loss of one star's mass sends the other hurtling away like a released rubber band. Others could be intergalactic intruders hurled our way by collisions between dwarf galaxies. The fastest known, S5-HVS1, was caught in the act of fleeing the Milky Way at 3.7 million miles per hour, a speed that would take it from Earth to the Moon in under 5 minutes. What happens to these runaway stars? Their futures are lonely. Stripped of their galactic homes, they'll drift through the void, their light fading over eons. A few might eventually collide with other galaxies, but most will wander indefinitely, their trajectories altered only by the faint tug of dark matter or chance encounters with molecular clouds. Yet even in exile, they serve a purpose, By tracing their paths backward, astronomers can map the Milky Way's gravitational field and even pinpoint the location of our own supermassive black hole, Sagittarius, a star. These stellar speedsters are more than curiosities, they're proof of gravity's capricious power. One moment, a star is bound to a companion. The next, it's catapulted into the abyss, a testament to the chaos lurking at the heart of every galaxy. And somewhere out there, right now, another star might be feeling the black hole's pull, poised to become the universe's next great escape artist. Gravity doesn't just bend light, it turns the cosmos into an artist, painting halos of fire in the darkness. These masterpieces are called Einstein rings, and they're some of the most striking proofs of general relativity in action. Imagine a distant galaxy billions of light years away, its light traveling across the universe only to encounter a massive foreground galaxy or cluster squarely in its path. Instead of being blocked, the light wraps around the object like water flowing around a stone, warped so perfectly it forms a radiant circle in the sky, a cosmic bullseye forged by gravity's invisible hand. The first full Einstein ring was discovered in 1998, but the phenomenon had been predicted decades earlier. Einstein's math showed that when two celestial objects align exactly along our line of sight, the foreground mass acts like a lens, bending the background object's light into a complete ring. The effect requires near-perfect symmetry, making these rings incredibly rare. Most gravitational lensing produces smears or arcs like in the Hubble Space Telescope's famous cosmic horseshoe. But when conditions align just right, nature delivers a flawless circle of light. One of the most stunning examples is the molten ring, officially known as GL Clues 0220170581. Captured by Hubble in 2020, it glows like a golden loop suspended in space. The foreground galaxy cluster's gravity magnifies the distant background galaxy's light nearly 30 times, revealing details astronomers would never spot otherwise. This isn't just a pretty picture, it's a natural telescope letting us study galaxies from the universe's toddler years with impossible clarity. Why rings, though? It's all about perspective. Just like holding a wine glass in front of a candle projects a ring of light on the table, the spherical symmetry of a massive lensing object bends light equally in all directions, focusing it into a circle. Tilt the alignment slightly, and the ring breaks into arcs or multiple images, but when everything lines up with celestial precision, the result is a halo so perfect it feels almost surreal. Einstein rings aren't just cosmic eye candy, they're tools. By measuring these rings' sizes and distortions, astronomers can map the distribution of mass in the lensing galaxy, including its invisible dark matter. They've even used rings to estimate the universe's expansion rate, adding another piece to the puzzle of dark energy. And in a breathtaking twist, some rings reveal multiple background galaxies lensed at once, stacking halos like jewels on a necklace, a reminder that gravity's artistry knows no bounds. The rarest of these phenomena are double Einstein rings, where two distant galaxies lie directly behind a foreground mass, creating concentric circles like ripples in a pond. Only a handful have ever been found, each one a time capsule of cosmic alignment. The most famous, SDSS J0946+1006, showcases galaxies from three different eras frozen in a single frame, a gravitational hall of mirrors spanning billions of years. What's truly humbling is that every Einstein ring we see is a snapshot of the past. The light forming those rings began its journey before Earth existed, twisted into a halo by gravity's patient hand, and now reaches us as both a relic and a revelation. They're proof that even in the vast chaos of the cosmos, gravity weaves order, a fleeting symmetry written in light, waiting for us to look up and see. Deep in the cosmos, nature's most precise timekeepers are whispering secrets about gravitational waves, and their rhythmic pulses are the key. Pulsars, the rapidly spinning corpses of massive stars, act like celestial metronomes, beaming radio waves toward Earth with such regularity you could set your watch by them. Some rotate hundreds of times per second, their flashes arriving like clockwork across millions of light years. But occasionally, something disrupts their perfect rhythm, not a flaw in the pulsar, but a ripple in space-time itself. When gravitational waves pass between a pulsar and Earth, they stretch and compress the fabric of space in their path. This infinitesimal warping alters the distance the pulsar's signals must travel, causing its pulses to arrive a few nanoseconds early or late. Imagine a drummer whose beats arrive slightly off rhythm because unseen hands are stretching and squeezing the air between you. That's what astronomers have been detecting for decades using networks of pulsars called timing arrays. By meticulously tracking these microscopic deviations across multiple pulsars, they can reconstruct the gravitational waves passing through our corner of the galaxy. The breakthrough came in 2016 with observations of pulsar J437-4715. Over a decade, its pulses drifted off schedule by just a few hundred nanoseconds, a deviation smaller than the blink of an eye, but enough to betray the presence of low-frequency gravitational waves likely generated by supermassive black hole binaries. These aren't the sharp chirps LIGO detects from stellar mass collisions, but a deep cosmic hum, like the background static of the universe. What's astonishing is the scale of these waves. Unlike the high-frequency ripples from black hole mergers, these undulations can take years or even decades to pass by, with wavelengths so long they could span the entire solar system. They're thought to come from the slow-motion dance of black holes billions of times the sun's mass, orbiting each other in the hearts of distant galaxies, their gravitational waves weaving through the cosmos like the bass notes of a cosmic symphony. Pulsar timing arrays are now hunting an even grander prize, the stochastic gravitational wave background, the combined ripples from all merging supermassive black holes in the universe. It's like listening for the murmur of a crowd rather than individual voices. Detecting this background would open a new window onto some of the universe's most enigmatic giants, revealing how often galaxies merge and how these monstrous binaries finally collide. But pulsars don't just sense gravitational waves, they help test gravity's fundamental nature. Some theories predict subtle differences in how gravitational waves should affect pulsar timing versus what Einstein's relativity predicts. If pulsars ever reveal a discrepancy, it could hint at new physics, perhaps even clues about dark energy or extra dimensions. Every nanosecond of deviation is a coded message waiting to be deciphered. So while these cosmic lighthouses may seem like relics, they're actually frontier observatories, their steady beats tracing the invisible warps and wefts of spacetime itself. The moon might seem like a silent bystander in the night sky, but its gravitational pull is engaged in an epic, slow-motion tug of war with Earth, one that's stretching our days longer, millisecond by millisecond. This relentless drag, known as tidal friction, has been quietly reshaping our planet's rotation since the Moon first formed over 4 billion years ago. Back then, Earth spun so rapidly that a single day lasted just 18 hours, with hurricanes howling at unimaginable speeds and the planet bulging at its equator like a ballerina mid-twirl. But the Moon's gravity acts like a cosmic brake, its invisible grip tugging at Earth's oceans and even its solid crust, gradually slowing our spin like a wheel grinding against resistance. Here's how it works. The Moon's gravity doesn't pull evenly on Earth. The side of our planet facing the Moon feels a stronger tug than the opposite side, stretching Earth slightly into an oval. This distortion creates tidal bulges not just in the oceans where we see high and low tides, but in the rocky mantle beneath. As Earth rotates, these bulges move, but the Moon's gravity tries to hold them in place, creating friction that saps our planet's rotational energy. The result, Earth's spin slows by about 1.7 milliseconds per century, a tiny but relentless change that adds up over geologic time. The evidence for this slowdown is written in fossilized coral and ancient sediments. By studying growth patterns in 500-million-year-old coral fossils, scientists discovered that Earth once completed 420 rotations in a single orbit around the Sun, meaning a year contained just 420 days, each a brisk 18 hours long. Even more astonishing, fossilized tidal records from 90 million years ago suggest days were roughly 30 minutes shorter than today. These aren't just curiosities, they're snapshots of a planet caught in a gravitational dance with its satellite, one that's still unfolding. But the Moon isn't just slowing us down, it's also paying a price. In a cosmic trade-off, the energy Earth loses gets transferred to the Moon, boosting its orbit by about 3.8 centimeters per year. Over billions of years, this has pushed the Moon from a close neighbor orbiting just 15,000 miles away to the distant companion we see today, 238,000 miles out. The process will continue until Earth's rotation syncs perfectly with the Moon's orbit, leaving one side of our planet forever locked facing the lunar surface, just as the Moon already shows only one face to us. What does this mean for the future? If humanity lasts another 100 million years, our descendants will witness days stretching to 25 hours, their sunrises creeping later as the Moon drifts farther into space. But this gravitational tango isn't unique to Earth. Similar tidal forces have locked Mercury into a spin-orbit resonance with the Sun and slowed Venus's rotation to a sluggish backward crawl. Even Pluto and its moon Charon have achieved mutual tidal lock, forever staring at each other across the void. So the next time you watch the tides roll in, remember, you're witnessing more than just water moving. You're seeing gravity's patient handiwork, a force that reshapes worlds across eons, turning the cosmos into a clockwork ballet of push and pull, spin and slow down. And in that grand celestial rhythm, Earth's lengthening days are just one small beat in an infinite cosmic song. What if every black hole is a cosmic escape hatch, a portal to an entirely new universe with its own laws of physics? This mind-bending idea isn't science fiction. It's a serious hypothesis some physicists call black hole cosmology. Here's how it works. When matter collapses into a singularity, the extreme conditions might not just crush reality. They could reboot it, sparking a big bang-like explosion that births a fresh cosmos inside the black hole's depths. Our own universe could be one such offspring, nested inside a black hole from a parent universe we'll never see. The math behind this is as elegant as it is radical. Einstein's equations show that a singularity's infinite density marks the boundary where spacetime itself breaks down. But what if that boundary isn't an end, just a transformation? Some interpretations of quantum gravity suggest the singularity's crushing pressures could trigger a bounce, where collapsing matter rebounds outward in a new expanding universe. The black hole's event horizon from the inside would look identical to our observable universe's cosmic horizon, the point beyond which light hasn't had time to reach us. We might already be living inside a black hole without realizing it. This idea gains traction when you examine the eerie parallels between black holes and our cosmos. A black hole's entropy, a measure of its disorder, scales with the area of its event horizon, just like our universe's entropy appears tied to its cosmological horizon. Even stranger, the universe's expansion accelerates in ways that mirror how a black hole's interior stretches under intense gravity. Could these similarities be cosmic coincidences or clues? Not everyone's convinced. Critics argue there's no mechanism to explain how information from the parent universe could transfer to the new one without violating thermodynamics. Others point out that even if daughter universes form inside black holes, we'd have no way to observe them. They'd be causally disconnected from our reality. But proponents counter that subtle imprints might linger. The cosmic microwave background's irregularities, for instance, could carry echoes of our parent black hole's violent birth. The most provocative version of this theory comes from physicist Lee Smolin, who suggests universes could evolve through a form of cosmic natural selection. Universes that produce more black holes would spawn more offspring, passing down traits like finely tuned physical constants. In this wild scenario, our universe's laws might be optimized for black hole production because we're the descendants of a prolific lineage, a fractal multiverse where gravity is both destroyer and creator. Whether this holds water or not, the idea reshapes how we view black holes. They're not just graves for matter, they could be cosmic wombs birthing realities where time, space, and physics itself begin anew. And if that's true, somewhere out there, in the heart of a singularity we'll never see, an entire universe might be unfolding unaware that its origin lies in our sky, in the dark eye of a gravitational storm. Gravity doesn't just bend light, it reveals secrets about the universe's most elusive substance. When astronomers peer at distant galaxies, some appear stretched into surreal arcs or smeared across the sky like celestial taffy. These aren't camera glitches or cosmic accidents, they're gravitational lenses, distortions caused by immense concentrations of mass warping spacetime itself. But here's the twist. Often, the amount of visible matter in these lensing galaxies falls far short of what's needed to create such extreme distortions. Something invisible is amplifying gravity's grip, and that something is dark matter. Take the galaxy cluster Abell 1689, one of the most powerful natural lenses ever discovered. Its gravity magnifies and twists the light of galaxies behind it into a spiderweb of luminous streaks. By mapping these distortions with near-surgical precision, astronomers reconstructed the cluster's mass distribution and found that over 80% of it doesn't correspond to any visible stars or gas. Instead, it traces the ghostly outline of dark matter, an invisible scaffold shaping the cosmos from the shadows. The technique works because dark matter, while utterly transparent to light, still exerts gravitational pull. When its unseen mass clumps around galaxies or clusters, it bends passing light just like ordinary matter, only more so. By studying how lensed images stretch and multiply, scientists can reverse engineer dark matter's hidden architecture, revealing vast halos that extend far beyond a galaxy's luminous edge. Some of these halos span millions of light years, their gravitational fingers intertwining in a cosmic web that guides the universe's large-scale structure. One of the most dramatic proofs came from the Bullet Cluster, two galaxy clusters caught mid-collision. When astronomers combined visible light images with gravitational lensing maps, they found something startling. The cluster's gas visible in X-rays had slammed together and lagged behind, while the bulk of the mass, guided by dark matter, had sailed straight through like a phantom freight train. This cosmic snapshot proved dark matter isn't just theoretical, it's a dynamic, collisionless substance that moves independently of ordinary matter, its presence etched into spacetime's very curvature. But lensing does more than confirm dark matter's existence, it exposes its quirks. Some dwarf galaxies, for instance, appear to have unusually diffused dark matter halos, while others, like Dragonfly 44, are almost entirely dark matter with few stars. Then there's the bizarre case of Galaxy NGC 1052DF2, which seems to lack dark matter entirely, flouting expectations and forcing scientists to reconsider how galaxies form. Each anomaly is a clue, hinting at dark matter's particle properties or even challenging our understanding of gravity itself. The next frontier, subtler distortions called weak lensing, where thousands of galaxies appear ever so slightly stretched by dark matter's pervasive pull. Projects like the Vera-C Rubin Observatory are mapping these minute warps across billions of galaxies, constructing the largest dark matter maps ever made. These surveys could finally answer whether dark matter is cold, warm, or something stranger, and whether it interacts with itself in ways we've yet to imagine. So while dark matter remains invisible, its gravitational signature is written across the sky in arcs and ripples of light. Every distorted galaxy, every Einstein ring, is a message from the universe's hidden architect, and with each lensed photon we catch, we're one step closer to decoding its secrets. Gravity doesn't just pull, it moves, and when it does, it races across the cosmos at the ultimate speed limit, the speed of light itself. This staggering fact was confirmed in spectacular fashion on August 17, 2017, when astronomers witnessed two neutron stars collide 130 million light-years away. For the first time in history, both gravitational waves and light from the same cosmic cataclysm reached Earth separated by just 1.7 seconds after traveling side by side for over 100 million years. That near-perfect synchronization proved what Einstein predicted a century earlier. Gravity doesn't act instantly across the universe. It propagates as ripples in space-time, bound by the same universal speed limit as light. Think about what this means. When the sun suddenly vanished, we wouldn't just float away immediately. Earth would continue orbiting nothing for 8 minutes, the time it takes light and gravity's influence to travel from the sun to us. The planets wouldn't feel the sun's disappearance until those gravitational waves arrived, like boats continuing to circle long after the whirlpool source has drained away. This delayed reaction is built into the universe's fabric, a fundamental limit that keeps cause and effect from getting scrambled across cosmic distances. The neutron-star collision that proved this was no ordinary event. Dubbed GW170817 after the gravitational wave signal that announced it, the merger sent both ripples through spacetime and a fireworks show across the electromagnetic spectrum. Gamma-ray telescopes detected the initial burst just after LIGO and Virgo's gravitational wave alerts. Over days and weeks, observatories worldwide tracked the aftermath. The glow of heavy elements like gold and platinum forged in the merger's intense heat, a kilonova explosion outshining entire galaxies for brief, brilliant moments. But the real revelation came from comparing arrival times. The gravitational waves and gamma rays weren't just close. Their 1.7-second gap matched theoretical predictions, accounting for how gravitational waves race through spacetime unimpeded while light interacts with interstellar gas. Had gravity moved slower than light, the delay would have been far longer, faster, impossible under relativity. This precise alignment was the smoking gun, proving both phenomena traveled at the same cosmic speed limit within experimental error. This discovery did more than confirm textbook physics. It opened new ways to test the universe's fundamental rules. Some alternative gravity theories predict slight deviations in gravitational wave speed, especially across vast cosmic distances. By timing future neutron star mergers, scientists could uncover evidence of extra dimensions or quantum gravity effects. Even tiny discrepancies might hint at physics beyond Einstein, hiding in the fractions of a second between gravity's whisper and light's shout across the cosmos. Yet the most profound implication is simpler. Gravity isn't magic. It's part of the same cosmic playbook as light, electricity, and magnetism. A force that plays by rules, moves at measurable speeds, and connects us to events so distant their ripples take eons to reach us. Every black hole merger, every neutron-star collision sends these whispers through spacetime, and now we know they race alongside light in the ultimate cosmic marathon, their speed stamped with the universe's deepest signature. And when the next collision lights up the sky, we'll be waiting stopwatches ready to decode gravity's message once more. Those breathtaking videos of astronauts floating effortlessly inside the International Space Station might look like they've escaped gravity's grip entirely, but here's the twist: they're not weightless at all. What we call zero gravity is actually a clever cosmic illusion. The truth, gravity up there is nearly as strong as it is on Earth's surface. If you could stand on a scale while orbiting 250 miles up, you'd weigh just about 10% less than you do right now. So why do astronauts appear to float? Because they're not fighting gravity, they're surrendering to it in the most elegant way possible: free fall. Picture this: the space station isn't hovering motionless above Earth. It's racing around the planet at 17,500 miles per hour, fast enough to complete an orbit every 90 minutes. At that speed, as Earth's gravity pulls the station downward, the planet's surface curves away at the same rate, creating a perpetual state of falling without ever hitting the ground. It's like a roller coaster cresting its first hill over and over, that brief sensation of weightlessness stretched into minutes, hours, months. The astronauts inside aren't beyond gravity's reach. They're caught in a delicate balance where Earth's pull keeps them circling while their forward motion keeps them soaring. This equilibrium is what scientists call microgravity, and it's one of the most misunderstood phenomena in space exploration. But don't take my word for it, try a simple thought experiment. Imagine tossing a ball straight ahead inside a moving train. To you, it arcs gently. To someone outside, it's also moving forward with the train's momentum, tracing a longer curve. Now scale that up. The space station is the train, Earth's gravity is your throw, and the curve is orbital motion. The ball, like the astronauts, seems to float because everything is falling together at the same rate. Even the pens, tools, and droplets of water in those viral videos aren't defying gravity. They're harmonizing with it in synchronized freefall. This isn't just physics trivia, it's the key to unlocking space travel. To reach other worlds, we don't need to cancel gravity. We need to master its rhythms. Consider how astronauts train for microgravity, not by escaping Earth's pull, but by mimicking freefall in vomit comet planes or underwater buoyancy labs. Even SpaceX's Crew Dragon capsule relies on this principle, its orbital dance a testament to gravity's unbroken hold. And here's the wildest part. If you could build a tower 236 miles high, the altitude of geostationary orbit, stood on top, and stepped off, you'd enter that same weightless freefall, because at that height, your sideways speed from Earth rotation would match orbital velocity. Gravity would still be tugging at 90% of its surface strength, yet you'd float like the astronauts. So the next time you see footage of life aboard the ISS, remember, those astronauts aren't in a gravity-free zone. They're performers in a celestial ballet with Earth's invisible strings guiding every pirouette. And down here, every falling leaf, every diver mid-air, every roller coaster cresting its peak gives us a fleeting taste of the same physics that keeps the heavens in motion. Microgravity isn't the absence of force, it's the art of falling with style. Imagine if the entire universe, every star, planet, and black hole, were nothing more than an incredibly convincing hologram. Not a science fiction simulation, but a fundamental property of reality where gravity itself emerges from information scribbled on a distant, two-dimensional surface. This isn't just wild speculation, it's a serious idea in theoretical physics called the holographic principle, and it suggests that gravity, the force we feel every day, might not be fundamental at all. Instead, it could be a shadow, an illusion cast by data processing happening on the universe's outermost boundary. The origins of this mind-bending concept trace back to black holes. In the 1970s, physicist Jacob Bekenstein discovered something revolutionary. A black hole's entropy, a measure of its information content, is proportional not to its volume but to the area of its event horizon. This was bizarre. In everyday systems, entropy scales with volume. Think of how much information you can store in a three-dimensional hard drive. But black holes seem to follow different rules, as if their information was painted on their surfaces rather than stuffed inside. Decades later, string theorists Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might work the same way, that all the information describing our 3D reality could be encoded on a 2D surface at the cosmic edge. Here's how the holographic principle might explain gravity. Picture the universe as a giant movie screen. The images projected on it, galaxies, planets, you appear three-dimensional, but they're actually just data rendered from pixels on the screen's flat surface. Gravity, in this view, isn't a force radiating through space. It's a byproduct of how that information interacts and evolves on the boundary. When you drop your keys, their fall isn't caused by space-time curvature, but by data updates propagating through the cosmic code. The implications are staggering. If gravity emerges from information, it could unite quantum mechanics and relativity in a way no other theory has. Quantum physics governs the behavior of information, while general relativity describes gravity as space-time geometry. The holographic principle bridges them by suggesting space-time itself is built from quantum bits like a 3D video game emerging from 2D code. This idea gets concrete in something called the AD/CFT correspondence, a mathematical framework where a higher dimensional universe with gravity, like ours, precisely mirrors a lower dimensional universe without it. Critics argue the holographic principle remains untested, and its math works cleanly only in simplified, hypothetical universes, not our messy, expanding one. But supporters point to tantalizing clues. Black hole thermodynamics, for instance, hints that information can't be destroyed, only redistributed, a hallmark of holography. Even the cosmic microwave background's fluctuations show patterns that some theorists argue could reflect underlying 2D information structures. So what would it mean if gravity truly is holographic? For starters, it could explain why gravity is so weak compared to other forces. It's not a fundamental interaction but a derived effect, like how the pixels on your phone create the illusion of depth. It might also resolve black hole paradoxes where information seems to vanish into singularities. If that information is always preserved on the event horizon, the universe never really loses anything, it just gets reprojected. The wildest possibility, our whole perception of three-dimensional space could be a grand illusion, with gravity acting as the glue that makes the hologram feel solid. Falling objects, orbiting planets, even the curvature of space-time, all might just be the universe's way of rendering its underlying data. And if that's true, then the next time you trip and feel gravity's pull, you're not just interacting with a force, you're witnessing the universe recalculating its code in real time. Every story has an ending, and the universe's final chapter will be written by gravity, not as the hero, but as the force locked in an epic tug of war with its shadowy rival, dark energy. Right now, as you watch this, an invisible battle rages across the cosmos. On one side, gravity pulls galaxies together in a slow cosmic dance. On the other, dark energy pushes space itself apart with increasing voracity. The outcome of this struggle will determine whether our universe meets a fiery collapse, a frigid disintegration, or eternal expansion into ever-deepening darkness. Let's start with the most dramatic finale, the Big Crunch. Picture the universe reversing its expansion like a film played backward. Galaxies stop fleeing from one another and begin rushing together instead. Gravity, no longer counterbalanced by dark energy's repulsive push, becomes the ultimate victor. Clusters merge in violent collisions, stars crowd the shrinking sky, and temperatures soar as cosmic background radiation blue shifts into deadly gamma rays. Eventually, all matter, every atom, every black hole, every shred of space-time collapses into a single point of infinite density, a mirror image of the Big Bang. Some theories suggest this singularity could spark a new universe in an endless cycle of cosmic rebirth, while others see it as a true end to reality itself. Now consider the opposite extreme, the Big Rip. Here, dark energy doesn't just win, it escalates. As the universe expands, dark energy's strength grows until it overwhelms not just galaxies, but stars, planets, and eventually atoms themselves. First, galaxy clusters are torn apart. Then individual galaxies unravel, their stars flung into the void. As the acceleration intensifies, planetary systems disintegrate. In the final moments, even atomic nuclei are shredded by the runaway expansion, reducing all matter to isolated particles drifting in a space-time fabric stretched so thin it loses all meaning. Time itself may cease to have any coherent flow in this scenario, leaving the universe as a freezing, empty wasteland where not even light can bridge the gaps between what remains. Between these cataclysms lies the most likely current scenario, the heat death. Dark energy maintains its dominance, but without growing stronger, allowing gravity to keep local structures intact while the cosmos expands forever. Stars burn out one by one, black holes evaporate via Hawking radiation, and matter itself decays over unimaginable timescales until the universe reaches maximum entropy, a state where no energy can flow, no work can be done, and no new structures can form. It's not violent like the Big Rip or cyclical like the Big Crunch, but a slow fading of all warmth and light into perfect equilibrium. Yet these scenarios aren't set in stone. The fate of everything hinges on dark energy's true nature, whether it's a constant force, Einstein's cosmological constant, or something dynamic that could weaken or strengthen over time. Recent measurements of supernova and the cosmic microwave background suggest dark energy's density has remained steady, favoring heat death. But just a slight change could tilt the balance, a possibility that keeps cosmologists awake at night. Some theories even propose that dark energy could eventually reverse sign, becoming attractive and triggering a big crunch billions of years from now. What's truly humbling is that this battle isn't some distant future abstraction. It's happening right now in every cubic light-year of space. The galaxies we see rushing away today are writing the opening lines of the universe's final story, with gravity and dark energy as opposing authors. And while we may never witness the ultimate conclusion, understanding this cosmic struggle changes how we see our place in time, not as permanent residents of an unchanging universe, but as fleeting witnesses to its grandest, most fundamental transformations. One day, whether through crunch, rip, or fade, gravity will have the last word, or be silenced forever. From black holes that stretch stars into cosmic spaghetti to rogue singularities drifting unseen through the galaxy, gravity isn't just a force, it's the universe's ultimate sculptor. Over these 30 facts, we've seen how it bends time like taffy near neutron stars, how it whispers secrets through pulsar beats, and how it might even be leaking into hidden dimensions we can't perceive. Gravity doesn't just hold galaxies together. It tears them apart in tidal disruption events, births new universes inside singularities, and wages a silent war against dark energy for control over cosmic fate. Think about the sheer range of its power. On one end, a teaspoon of neutron star material weighs more than Mount Everest. On the other, the Great Attractor yanks entire galaxy clusters toward oblivion with the force of tens of thousands of Milky Ways. Gravity slows clocks on GPS satellites by milliseconds and stretches seconds into eternities near black holes. It turns quasars into lighthouses brighter than 1 trillion suns and paints Einstein rings across the void like celestial bullseyes. And lurking in the shadows, primordial black holes smaller than atoms, rogue singularities ejected from galactic centers, and maybe, just maybe, white holes vomiting matter into unborn universes. Yet for all we've uncovered, gravity's extremes keep defying expectations. Why do supermassive black holes grow so fast in the early universe? What's the true nature of dark matter's gravitational grip? Could holographic gravity rewrite the rules entirely? Every discovery peels back another layer, revealing how much we still don't understand about the force that shapes existence itself. So here's my challenge to you. Which fact bent your mind the most? Was it the quantum possibility that we're all living inside a black hole? The rogue singularities that could sneak up on us undetected? Or the chilling reality that dark energy might one day rip space-time apart? Drop your thoughts in the comments, and while you're at it, take a guess. What gravitational mystery do you think scientists will crack next? The cosmos is full of surprises, and gravity's strangest chapters might still be waiting to be written. Until then, keep looking up. The universe's most extreme forces are out there, warping reality in ways we're only beginning to imagine.